Good morning, everyone. Let's continue with our discussion of kinetics, where here we're going to stop directly talking about kinetics and we're going to start talking about something that kinetics is very useful for determining. Okay, so I guess after having a whole discussion on kinetics and how fast reactions go and the activation energy and the frequency factor, you may start asking the question of, why is this so important? Okay. Well, there's something in chemistry called a reaction mechanism. Okay. And this comes about because most reactions do not occur in one step. Okay, but over the course of many steps. Okay, this means that reactions don't typically happen the way that we write them out. Okay, let's consider a reaction between hydrogen and chlorine gas, or iodochloric acid. Wait, what is that? Oh, excuse me. It's iodine monochloride. Pardon me. So let's consider the reaction between hydrogen gas and iodine monochloride. That's kind of a weird chemical. Reacting to form HCl and iodine gas. Okay? Let's consider this reaction. Given this information up here, we can basically assume that this mechanism does not occur in one step, but it's going to occur over several steps. Okay? What we draw here is the overall reaction. Okay, this is the total result of the chemistry that's happening here. But it doesn't necessarily mean this is exactly how the chemistry happens. What we want to do is we want to figure out exactly what chemistry is happening, because this part only shows what's in the at beginning and at the end. It doesn't show any information about what's happening in the middle. Okay, that's what we want to know. Okay, so a reaction mechanism, more specifically, is a series of individual steps by which an overall reaction occurs. Okay, so it's a series of steps that sum to the total reaction, and these are called elementary steps. Okay, so for this reaction above, we have step 1. Step 1 involves the reaction of one hydrogen molecule with one iodine monochloride molecule to form hydroiodic acid and HCl. Okay, that's the first step. Now, notice here right away, hydroiodic acid is nowhere in this overall reaction. Okay, there is no hydroiodic acid here, and so we've already come to a point where we have something that's not around in the overall reaction. Okay, that's interesting. We'll come back to that in just a second. Okay, so then there's a second step where hydroiodic acid reacts with another iodine monochloride molecule to form another hydrochloric acid molecule plus an iodine gas molecule. Okay. Now these are the two steps. We can just sum them together and we should get the overall reaction. Okay. As you'll notice, the hydroiodic acid is present on both sides of the equation, so it goes away. Everything else sums together, and we get the total reaction of H2 gas plus ICl gas goes to, oops, there's 2 ICl gas. Let's make that a little neater. Goes to 2 HCl plus iodine gas. Okay. This sums to the total reaction that we saw above, or the total overall reaction that we have above. But as you can see from these two elementary steps, it's actually, the chemistry is actually happening in 2 steps. Okay. Another interesting bit is that HI, or hydroiodic acid, appears in the mechanism, but not in the overall reaction. Okay. This is called a reaction intermediate. You'll notice that it's produced in the first step and it's consumed in the second step. Okay. So when you produce something in the first step or in the third step and then you consume it in a later step, it's called a reaction intermediate, and it does not show up in the overall reaction. Okay. So reaction intermediate is always formed in one elementary step and consumed in another. Okay, so this here is the reaction mechanism for this overall reaction above. Okay, so this is the reaction mechanism, and this is the complete chemical picture for what's actually happening. Okay, so it's the complete molecular or chemical picture of what's happening, and as you can imagine, this is very important to chemistry because this is telling us exactly what chemistry is occurring in an overall reaction. Okay, it's not necessarily the way it's written out. It can actually occur in very strange and different ways than what is actually written out. Okay. And the way that we figure out what's actually happening is kinetics. You can imagine that each one of these steps is going to have some rate constant associated with it, and because of that we can determine using kinetics what is actually happening during a reaction. Okay, which makes kinetics extremely useful. Okay, so let's write out what exactly we can do with kinetics in regards to figuring out the reaction mechanism. Okay, so each one of these elementary steps that make up the mechanism, we can define a rate law for each of these steps. Okay, and this is characterized by something called molecularity. Molecularity is the number of reactant particles involved in each elementary step. Okay, so the molecularity is simply the number of reactant molecules in each elementary step. Okay, so if we have, for example, the generalized elementary step going from A to product, this would be a unimolecular step. Okay, if we have A and A going to products, this is a bimolecular step. If we have A plus B going to products, this is also a bimolecular step. If we have 3 going to the products, this is a termolecular step. Okay, and it turns out that termolecular steps are extremely rare. Okay, and you can imagine why. Because in a reaction mechanism, we are talking about the direct interaction of these 3 different pieces. That means that all 3 of these pieces need to be in the exact same spot at the exact same time. And you can imagine, if you think all the way back to kinetic molecular theory for gases, these things are bouncing around all over the place, and to have 3 things in one spot at one time is actually an extremely rare event. Okay, so when something is extremely rare, that means that from a statistical or a kinetics standpoint, it's not really going to happen very often. Okay, you're not going to have many processes that are dependent on a termolecular elementary step, simply because statistically it doesn't happen often enough. Okay, but every once in a while it does. Okay, so remember back when I told you that we can't deduce rate law, the rate law for a reaction. Oh, well, maybe I should go ahead and call this overall reaction by simply looking at it. Okay, we can't look at this overall reaction above and say, oh yes, this is going to be second order for sure. We can't say that, right? We can't say that. That's not allowed. There's no way for us to know what the order of that reaction is. However, it turns out that for elementary steps, this is possible. So if you look at an elementary step, you can determine the rate by simply looking at it. Okay, that's why it's so interesting or important to know the molecularity of the step, because the molecularity tells you what the rate law is. Okay, so if I have a bimolecular elementary step, I know that the rate is going to be equal to K times A times B, and it's going to be second order. If I have a bimolecular elementary step between A and A, I know that the rate is again going to be second order, and it's going to be K times A squared. Okay, and if I have a unimolecular elementary step, I know that my rate is going to be equal to K times A. Okay, so you can deduce the rate law by simply looking at the elementary step. This is not true for the overall reaction. Okay? It's not true for the overall reaction. It is true for the elementary steps. Okay? The elementary steps that make up the overall reaction, we can deduce their rate laws by simply looking at the reaction. Okay. And I guess it kind of makes sense here, but you can see from this that the rate that we produce is proportional to the number of reacting particles, or it's proportional to the molecularity. Okay. And just to reiterate, we can deduce kinetics from these individual steps. We can deduce these kinetics from individual elementary steps because they represent actual collisions. Let's call them actual molecular collisions. Okay? They represent actual molecular collisions, and because of this, we can actually deduce the kinetics just by looking at the reaction itself. Okay. And this all comes from a theory called, crazily enough, collision theory. Collision theory. Okay, so if we have some sort of reaction between a gas A and a gas B producing some product C. Two things can happen here. Number one, A can collide with B if they end up in the exact same spot in space, in time, and produce C. Or A can collide with B and A bounces off and B bounces off. Okay? In this case, no C is made. Okay? In this case, well, hold on, let's look at it from left to right. So in this case, a reaction occurs between A and B. In this case, no reaction occurs. And this is simply due to the fact that there's not enough energy to overcome EA. Okay. If you guys remember back to our discussion of the rate constant itself being proportional to this exponential factor times a frequency factor, okay, in the gas phase, we can start to realize or think about what this frequency factor actually means. So A, the frequency factor, is associated with the collision rate. Okay? It's associated with the collision rate. Basically, how many times per second a collision occurs. Whoa. Okay, and you can see that that would give you a proper description of A here. So you can have two cases, one where the reaction occurs and one where the reaction does not occur. So if you have trillions of collisions per second, right? Then that would determine your statistics of the reaction taking place or not. That would determine directly your rate constant. Okay, how many times per second these things are colliding, and the amount of activation energy that each of those collisions have to overcome in order for a reaction to take place. Okay, so an elementary step, what we've been talking about in terms of a mechanism, whoa. An elementary step depicts a collision between molecules. Okay. Okay, so within this idea of kinetics, there is something called, or there is something termed a rate limiting step. Okay, the rate limiting step. Now recall from above that each of these individual elementary steps have their own kinetics associated with them. That means since each of them have their own kinetics, they have their own kinetic rate constant, they have their own rate law. So each of them are going to be happening at a different rate. Okay. Now there is one particular step, and this occurs in most reactions. There is one elementary step is very slow compared to the rest. Okay, and this is called the rate limiting step. Okay, so it's very slow in comparison to the other steps, which means that it is the rate limiting step. So basically the rate limiting step determines, for the most part, it determines the kinetics for the entire overall reaction. Okay, consider something that I'm sure you guys have experienced before, although not recently because not many people are on the road these days. Okay, you guys have been traveling on the highway before, and you've come to an area where they've cordoned off 2 of the lanes, for example, and they put all 3 lanes into 1 lane. And as you're driving down the highway, by the way, these little boxes that I'm drawing here, these are cars. Let's make a safe traveling distance between them. Okay, now all of the cars at this point here have to funnel down into 1 lane. So it goes from 3 lanes to 1 lane. Okay, now the reason that this whole overall shift between 3 lanes, A plus B plus C, goes into just C, the reason this takes so long is because of this one step of going from here to here. Okay, so this is the rate limiting step, and it slows down the entire freeway. Okay, it slows down the entire freeway or highway, whatever you want to call it. So this is the rate limiting step for that occurrence when they close off these 2 lanes in the highway. You can imagine that this is also true with chemistry. There is a rate-limiting step within chemistry. And importantly, the rate-limiting step in chemistry, I'm not talking about the freeway anymore, I'm talking about in chemistry, determines the rate law for the overall reaction. So if we can, if we can just figure out the kinetics for the rate limiting step, we know the kinetics for the entire reaction, which is super useful, okay? And I'm going to break here, and when we come back for part 2 of today's lecture, we'll actually go through an example of this, and we'll show it written out in more detail, okay? See you then.